My name is Michael Spedding, and I'd like to talk today about something which is I've got quite strong feelings about, and we've done quite a bit of research on, which is the current status of research on aging, diseases associated with aging, and how we can better address them, and also how you can go ahead and link the physiology and metabolomics with many of the diseases. Now, I've been a pharmacologist for half a century, but even longer, I've been a competitive athlete. I was once international marathon runner, and I've been competitive for almost 60 years. What is more, my younger brother was English marathon champion, third in the Olympics, had the English marathon record for 25 years. And because I've been in good teams, I've been able to have links with very high level athletics, at the same time, very high level pharmacology. So this gives me a rather unique insight into the aspects of the interface between sport and pharmacology, and also aging. And I'd like to show you these and how it affects disease. So I'll just share the screen. So we all know, presumably, near Barzilai's work on the redundancy of diseases with aging, that the growth of the number of diseases goes up with the age-dependent diseases goes up, and that if one doesn't get you, another one will. Also males and females, and even if you therefore got rid of all cardiovascular disease, you would still only increase the lifespan of humanity by about 3 years. Now, this is a very important concept, and it goes with some of the other concepts I'm going to develop later on in this very quick talk. First of all, also you've got to look at this worldwide. The causes of death in healthcare are very different for high income and low income. These are non-communicable, communicable, and green injuries from WHO data. And you can see there's a big aspect about low income and where you live in the world. And so it's two worlds for healthcare and diseases. And according to this also, nobody dies of old age. But your capacity of reaching old age is also dependent upon your income and where you live. Now, we've made one of the main things I've been doing is keeping a list of protective effects for aging, and also the multiple changes associated with aging. I've given these in talks, but I'm not going to go into it. Just to point out the enormous list. It's adapted from Garante et al. And exercise. Actually, exercise can be associated with, at the best terms, almost 7 years of life expectancy over somebody who has got a very different form of lifestyle. So it has got some benefit. However, one of the things that I've been interested in as a pharmacologist also is that man may have evolved to run, and certainly to exercise. And Bramble and Lieberman published in that the fossil evidence indicates endurance running is derived from Homo about 2.5 million years ago, instrumental in the evolution of the human body form. And at the same time, we grew our brains. And walking, running was to heat shock prey at midday. And this therefore led to a lot of different changes in our bodies. And with one of the main athletic coaches in the world, Tim Noakes, and I, we had a little article in Nature about how humans are very different from other animals. We had a metabolic evolution to increase our VO2max, our capacity to use oxygen, in about 1 million years, 2 to 3 million years ago, that we may be metabolically optimized with evolution of brain size and circuits, and then very recent evolution, the last 200,000 years, to occupy all planetary niches for Homo sapiens, with a modern lifestyle and diet and diseases, which is a key thing. We actually claimed that, therefore, one of the factors which might have been important was brain-derived neurotrophic factor, which changes metabolism, opposes neurodegeneration, acts in the spinal cord to reduce heart rate, and it's got very many effects on immunity. We've shown on increasing the efficiency of brain mitochondria. Interestingly, now I'm going to show you a little bit that a glycosphingolipid, which may have evolved 2.5 million years ago, and binds to BDNF receptors, TrkB receptors, and also TrkA receptors, may actually have been very formative in this way. And so These are the changes which I keep a list of for body and metabolic effects in evolution. And I think these have got very much, these are very much crucial for how we can see our modern diseases. And I'm not going to go through them. Neuromuscular junctions have changed, major changes in liver metabolism to increase VO2max. One thing which I will just say a few words about, which is also going to be in our symposium on Wednesday, and also Elena Chiricosi in this meeting is going to talk about it. Viral infections also affect glycosphingolipids. And 2.5 million years ago, Varkey has shown that we actually, humans, dropped an enzyme, or humans without the enzyme survived a viral infection, which changes the sialic acid in GM1, which is a pentasaccharide glycosphingolipid. And they've timed it for about 2.5 million years ago. And that's a fairly crucial aspect. Otherwise, we also have great heat tolerance. And we're about the animal which can sweat up to 3.5 liters an hour. And I've actually done a very hard bike race at 35 degrees, and it's fine, but I drank 7 liters in 3 hours. And then, so we would also, because of delayed brain development in adolescence, a delayed aging, we might well be optimized for delayed aging compared with our metabolism. And Kaitovich, whose work I really admire in terms of metabolomics, has shown that the lipidome is the key way forward for differentiates us. And he's also said that there are divergences between human muscle and brain metabolomes in the brain areas which we particularly organized in terms of prefrontal cortex, etc. And he claimed that we might have sacrificed muscle strength for metabolism. I've analyzed it. I think it's probably muscle endurance rather than strength. But these are lipid changes which are very crucial for metabolism and VO2max, oxidative capacity. And so, and also it's been confirmed that humans have got a higher metabolic acceleration, which is it's quite rare to be able to have an increased metabolism and a longer lifespan. So I therefore worked with the INSEP, which is the main French sports science group, and co-chaired Adrien Marc as a wonderful PhD student. And we analyzed age records in people for 100 and 800 meters marathon and all sports effectively. And the data are absolutely amazingly precise in the decline. And it fits 2 simple exponentials, up and down. And the correlation coefficient with these links is 0.09 for one sport, which means that there's no getting out of it. Obviously, the speeds here are different, depending upon whether you're doing 100 meters, 800 meters, or a marathon. However, there's an interesting aspect that was published that if you look at chest scores and all facial recognitions, cerebral activity, then it's also amazingly tight, and there's a decline, which is fairly similar. But in a chest score, this is the ELO score. These are grandmasters because it's the best in the world. That's just a face recognition score of age. But they're still at 80 years old, despite having some decline, of ELO score of 2,500. And that will win many national championships or get you very close. So that means the brain's partially protected in its functioning, assuming you don't get a disease, as these people presumably are the healthiest expression of 800 million, of 8 billion people. We studied this for in a whole variety of papers. This relationship was shown by Dan Moore in Nature in 1975, and we defined it. We believe that we're reaching about the limits of Homo sapiens for the last 30 years. We don't, even in veterans athletics, we don't see a real improvement. There are small improvements. There's actually been a big improvement recently, about 30 seconds for 10,000 meters, almost 4 minutes in marathon for running shoes. But that's a technical, it's not Homo sapiens improvement. And so we believe there's age-related limits. And so, therefore, I'd like to, the 5,000 meters is a sport I particularly like. And it's the best test of VO2 max because you're at VO2 max for about 97% of the race if you're doing a fast time. And VO2max is the maximum mitochondrial capacity. And when you look at men and women, there's a really precise decline. Even Michael Spedding, over all these years, has kept within 15% of speed of the age best for 5,000 meters, the age best. And there's a small link here that's due to Olympic class athletes giving up when they've won the 40 to 42-year-old veterans class. When you put it as a percentage best speed, it's even more, absolutely amazingly precise. And men and women are therefore overlay each other, which means probably that the difference in athletic performance is not related to the difference in age dependency. Also, COVID-19 and flu, the age dependency of this tracks down with your loss in oxygen capacity. I believe this is very important. And why? Because it's also, on Wednesday, we're having a seminar on glycosphingolipids, which are crucial also for infection of envelope viruses. And all these envelope viruses, dengue, Ebola, etc., require glycosphingolipids in lipid rafts to get in. And then when they get in, they must make their viral replication, and their envelopes are taken from our endoplasmic reticulum and actually consist of cholesterol and glycosphingolipids from our membranes. And the glycosphingolipids are made in the endoplasmic reticulum and Golgi and go out and then go via the lysozyme. So glycosphingolipids are actually critical for both viral infection, and I'll show you later, for some neurodegenerative disease. And Rishika Pereira, who we collaborate with, has shown in electron microscopy, this is dengue, but the same for SARS, that in viral infection, here you see the mitochondria in the host cells, the viruses just take over the endoplasmic reticulum, causing a massive endoplasmic reticulum stress, and also just totally take over the endoplasmic reticulum. Now that means also that the mitochondrial associated membranes are going to be remarkably damaged, and therefore it's probably one of the reasons why COVID is such an oxygen-dependent disease. And Rishika has also shown that really amazing changes in the metabolomics of these cells, and particularly lipid metabolism. And we've shown that ceramide, glucosylceramide, ceramide is identified for a major node for viral release, SARS-CoV-2 and dengue. You'll see it's important as well. And so this shows the VO2max of the best human athlete at present, 94. I'm about 50 now. There is the best cyclist who made age-dependent records between 100 and 105 had a VO2max of 35. But a 73-year-old in a nursing home has only got a VO2max of about 13. So there's no oxygen reserve at all for somebody to be infected with COVID in a nursing home. And we've got a big grant now for looking at COVID-19 and neurodegeneration in long COVID. So these, and the precision of this running decline is therefore actually at least as good as what's claimed to be the best clock for human decline, epigenetic clocks, because it's what we're looking at is the best of the entire human race, the 8 billion people that want to compete athletically, which is a slight restriction, but nevertheless, it's a really important way forward. I believe it's got very major implications for aging research, because the simple exponential resembles the second law of thermodynamics. And Hayflick has argued very strongly that aging is just increasing entropy, and that would be the case. And if so, it's just disintegration of a complex system. So the reason you get all these different diseases is because aging just gives you disintegration of your control systems. And depending upon which particular factor goes wrong, or the environment, or your own personal genetic makeup, then you're liable to get one or another of the diseases. And it's inescapable. The precision of the decline is amazing to me, because I've wriggled on it for many years in terms of my running decline. It's got major implications for healthcare. It's also possibly dangerous to stress a disintegrating system. And at the inevitable end, there are multiple issues. And so it can be use it or lose it versus don't stress a disintegrating system. And there's also implications for the end of life and research, because if you are condemned to go out with a very low energy at the end, then possibly we need to think of ways of looking after yourself and helping people that are reaching this end. There's another issue, which I'm really upset about to a certain extent. If humans are optimized, what use to use short-lived species? Of all these massive number of papers claiming a small change in a short-lived species is probably not at all applicable to humans. And you've just got to see a lot of webinars or nature papers whereby massive resources have been thrown by very rich California companies on finding a cure for aging. There's probably not a cure for aging because we're optimized. And if 8 billion people with all diets, all races, can't find a way to increase that, push that graph up, it's very unlikely we're going to find something when exercise has already increased it as far as it can. But you can also use this for totally new ways forward into drug discovery and development. And that's what we've done with using what we thought about was metabolomics, and then a way into an impossible disease. So we had an ALS program whereby if mitochondria and lipid metabolism are crucial, then we ought to be able to see if that is involved in neurodegeneration. And Jean-Philippe Loeffler's group in Strasbourg, who've been a friend with for many years, and I just like to attribute my thanks to him and Alex Henriquez, who we had as a project leader between him and myself, has shown that energy metabolism and lipid metabolism completely changed in ALS. And so we looked at metabolomics, 3,000 lipidomics, thanks to Servier, and transcriptomics. We found ceramide glucosylceramide ratio critical in muscle and spinal cord, and also in human patient tissue. And we therefore screened on glucosylceramidases. We've used 3 different animal models with metabolomics and the TB43 with Brad Turner's group. And then we found an old drug, ambroxol, which has now got orphan drug designation, which started phase 2 a month before the WCP. It also preserves GM1 in nerve endings because the glycosphingolipids are also crucial for the breakdown of the 5-sugar GM1. This means that the neuromuscular junction at running, which we developed after GM1, and if you knock out CMAH, the enzyme which humans knocked out, and put it and knock out that in mice, Ellen Breen and Varkey have shown that it massively increases running capacity in mice and their oxidation. And so we have a reasonably good rationale based on these findings of evolution and also for viral infection. And we're now looking at, we've got this JPND grant for seeing whether there's a link between, for glycosphingolipids, seeing there's a link between long COVID and neurodegeneration. So you can see the work about this on Wednesday on our symposium. And therefore, that shows a practical way forward of addressing this, which isn't a way of looking at just old animals. So how do I manage to do this as an old athlete? Well, I actually had a heart problem from falling at high speed on the chest and damaging my papillary muscle, which has now stopped giving me a difficulty. And I actually think that one of the use it or lose it, but don't stress a disintegrating system is actually relevant to old athletes, because now, this was 3 years ago, now I've got quite a few friends who've had very difficulties continuing to force themselves running. So Max Wheatman, my PhD supervisor, was one of the people that invented metoprolol, the first beta-1 selective drug. And I used besoprolol. This is a dose response curve for me in reducing the effects on excessive heart rate stimulus, because I've been told by my cardiologist I can't. And so this is the control at sprints. And you can see 1 milligram, I've got a good heart rate response to speed of 12 by 150 meters. And at 1.25, which is the dose I take, I've got a good, nice heart rate response, but it's only limited to 120. Therefore, it's not stressing the heart while still being able to give speed. If I go beyond that, then my heart rate falls completely and the legs are asphyxiated. So I believe actually that there are ways of that why pharmacology can actually look for ways of increasing health care in aged athletes and possibly more in older people. The only, as I said, the only muscle that my physio can't help is my heart. Also, the other thing you've got to avoid are viral infections, because I've lost every time I get a serious viral infection, as you've seen from viral infections in mitochondria, I lose permanently 1 kilometer an hour on my ischemic, my threshold. And also, Paul Greenhoff, a great scientist in the UK, has shown how viral infection, how prolonged surgery can damage skeletal muscle. And this shows the massive inflation-driven muscle breakdown. And that shows avoid viral infections and surgery. So these are the messages I have. It's inescapable. You've got to accept it. If humans are optimized, what use to use short-lived species? And I think that's an area whereby you really should think about what we're doing in terms of looking for eureka-type responses. We should be able to modify the age-related diseases, but I don't think we're going to make humans live for much longer. And it's got implications also, ethical implications for the end of life, but also for research. So thank you very much for listening. And I look forward to discussing this with you during the meeting or arguing about it. And so thanks so much.